From rare materials created in particle accelerators to toxins harvested one drop at a time from venomous creatures, certain substances carry price tags that make gold seem inexpensive. Today we're exploring 5 of the world's costliest materials by weight, where just 1 gram can exceed the price of a high-end vehicle. Subscribe to the Record Vault to uncover more astonishing stories about the scarcest, most precious, and most remarkable substances found on our planet. Beginning at number 5, Taphite gemstone. Found by chance in 1945 when gemologist Richard Taffa discovered it among a collection of spinels. This exceptionally scarce gemstone stands as one of the rare minerals ever recognized from a cut stone instead of raw form, making it 1,000,000 times scarcer than diamonds with prices around $20,000 per gram for premium samples. The gem's extraordinary rarity results from its distinctive chemical makeup that needs beryllium, magnesium, and aluminum to form under highly particular geological circumstances, existing in just a few places globally, mainly Tanzania and Sri Lanka, with under 50 jewelry-grade pieces confirmed in personal collections. Taphite's delicate lavender to mauve hues result from trace amounts of iron and magnesium, producing an understated elegance that enthusiasts treasure specifically because so few individuals will ever encounter one personally, and the gem's double refraction characteristics make it particularly attractive to collectors who value its scientific rarity as much as its visual appeal. The Taphite market stays remarkably specialized, with most pieces quickly purchased by dedicated collectors prepared to spend top dollar for the prestige of possessing one of the planet's rarest gems. While mineral experts keep exploring known sites, hoping to uncover more examples that might assist researchers in learning more about the exact circumstances necessary for this enigmatic mineral's creation. Advancing to number 4, tritium. This radioactive hydrogen variant, carrying 2 neutrons rather than the standard 0, emits light perpetually without needing external power and runs about $30,000 per gram, proving essential for self-illuminating emergency exit signs, defense uses, and fusion experiments despite its 12-year half-life demanding regular renewal. Tritium manufacturing involves striking lithium with neutrons within nuclear reactors or extracting it from heavy water in particular reactor configurations, forming an exceptionally power-hungry and technically sophisticated production method that only select nations can execute at industrial levels, with America depending substantially on Canadian nuclear operations for its tritium requirements. The isotope's mild beta emissions scarcely pierce human skin, rendering it secure enough for everyday items like timepiece faces and firearm sights, where its distinctive green luminescence delivers lighting for decades without batteries, although authorities tightly regulate its application due to ecological worries about tritiated water polluting underground water sources if discharged in substantial volumes. Tritium's primary use continues to be thermonuclear armaments and fusion power studies, where it functions as fuel for hydrogen weapons and prototype fusion installations like ITER, with countries vigilantly protecting their tritium reserves as vital strategic materials, while researchers hurry to create improved manufacturing techniques for the fusion generators they anticipate will someday supersede fossil fuels. The material's blend of defense significance, commercial uses, and fusion capability guarantees demand will stay robust, even as manufacturing expenses slowly decline through technical advances, although its radioactive breakdown means no degree of cautious containment can stop steady depletion that demands continuous resupply. Proceeding to number 3, diamond, nanodiamonds, and rare colors. Though standard diamonds run thousands per carat, exceptionally scarce shades like red, blue, and pink can hit $1.5 million per gram, with the 1.92 carat Hancock red fetching almost $1 million per carat in 1987. Positioning these colored varieties among the planet's most precious natural materials due to geological flukes that captured particular contaminants during crystallization. Red diamonds derive their shade from structural distortion of the crystal matrix during creation under severe conditions, with merely 30 authentic red diamonds documented in existence, while blue diamonds obtain their color from boron particles that need crystallization at depths beyond 400 miles, where descending oceanic plates transport surface elements far into the planet's mantle. The Argyle operation in Australia, which shut down in 2020 following depletion of its reserves, supplied more than 90% of global pink diamonds, driving values for remaining gems skyward as buyers understood no major fresh supply would ever enter the marketplace, with certain analysts forecasting values might multiply threefold within 10 years, as affluent purchasers vie for a truly limited commodity. Ironically, researchers can now create perfect diamonds in labs at a minuscule portion of natural diamond expenses, generating an identity crisis for the jewelry sector that depends on manufactured shortage and sentimental promotion instead of genuine scarcity. Though colored diamonds stay challenging to replicate with uniform outcomes, maintaining their worth currently. The disparity between synthetic diamonds costing cents per carat and natural colored diamonds valued in millions demonstrates how human mentality prizes chance geological events over flawless human creation, guaranteeing that as long as consumers want uniqueness and natural heritage narratives, these scarce colored gems will demand extraordinary prices irrespective of their utilitarian purposes. Escalating to number 2, californium-252. This manufactured radioactive substance, produced exclusively by striking berkelium or curium with neutrons in dedicated nuclear installations, runs roughly 27 million per gram, and exists in amounts measured in grams globally, establishing it as among the strongest neutron generators accessible for commercial radiography, tumor therapy, and explosive detection. The substance's manufacture demands beginning with plutonium, converting it through multiple neutron absorptions and radioactive transformations that may require years to finish. With just 2 operations worldwide, Oak Ridge National Laboratory in America and the Research Institute of Atomic Reactors in Russia, able to generate it in significant volumes, and even these facilities create only hundreds of micrograms yearly. Californium-252's remarkable usefulness derives from its spontaneous splitting, where every microgram releases 170 million neutrons each minute without needing any external activation, proving indispensable for igniting nuclear reactors, examining mineral samples for concealed resources, managing untreatable tumors through neutron brachytherapy, and inspecting shipping containers for concealed nuclear substances at harbors. The isotope's 2.6-year half-life indicates buyers forfeit half their purchase to radioactive breakdown every couple years, whether or not they employ it, compelling purchasers to meticulously determine whether uses warrant the tremendous cost when less expensive options might work. Though for specific niche purposes, no alternative matches californium's distinctive characteristics. Protection around californium manufacturing and allocation stays incredibly stringent, considering its possible utility in radiological weapons or as a neutron trigger for atomic arms, with global agreements strictly controlling its movement across borders, while researchers keep investigating whether more productive manufacturing approaches could ultimately reduce expenses sufficiently to broaden its therapeutic and commercial implementations. Claiming the ultimate number 1 position, antimatter, the costliest material ever manufactured by humans, antimatter demands an estimated $62.5 trillion per gram to create, persists for tiny fractions of seconds before destroying with regular matter in explosions of pure energy, and signifies physics' supreme fuel if technicians could ever crack the seemingly impossible obstacles of manufacture, containment, and regulated discharge. Antimatter generation presently occurs at locations like CERN's particle smashers, where protons crash together at almost light velocity, occasionally yield matter-antimatter combinations. But the power needed to create even one antiproton surpasses the power discharged when it destroys by billions, rendering existing manufacturing approaches ridiculously wasteful and clarifying why civilization has manufactured only roughly 20 nanograms combined throughout recorded time. The material's destruction with regular matter transforms 100% of mass into power, following Einstein's renowned ERMC2 formula, versus nuclear splitting's 0.1% performance, establishing antimatter as the supreme energy generator if someone could determine how to produce it affordably and contain it without contacting any vessel surfaces, since any interaction with normal material triggers immediate reciprocal annihilation. Investigators have effectively confined separate anti-hydrogen particles for minutes employing magnetic forces in ultra-high vacuum compartments, chilled to near zero absolute, confirming containment is conceptually achievable. But expanding this to practical volumes would necessitate technical innovations that presently appear unattainable, like addressing the challenge of constructing an antimatter storage unit that doesn't obliterate the contents. The contradiction of antimatter is that although it provides boundless pollution-free power and would transform interstellar travel by supplying the supreme propulsion fuel able to reach neighboring solar systems, the principles of physics themselves appear to prevent its feasible application, demanding greater power to manufacture than it yields, and requiring containment answers that might be intrinsically unachievable, assuring it will probably stay the priciest and most impractical material on the planet for the predictable future, unless somebody locates a naturally existing antimatter reservoir or formulates groundbreaking fresh physics. These remarkable materials demonstrate that worth isn't solely about aesthetics or scarcity. Occasionally, it concerns the exceptional challenge of production, targeted uses, or basic characteristics that stretch the limits of physics and technology. Which of these costly substances astonishes you most? Post your opinions in the comments and don't forget to like and subscribe to the Record Vault for more captivating investigations of the extreme, the scarce, and the scientifically extraordinary.